quick.
Sorry about that.
Yeah. So basically here is an example of the OS 3100. As Dan said, it's an XML file, and you see some of the elements here, the description, the expression as it's brought into the dialog boxes of Nlight. So these things can be modified, as Dan said, for any type of sensor for which there isn't an existing template.
And what I typically do is take one that's similar to the new sensor that I'm going to create and use it as a starting point and modify it, and makes it a lot easier than trying to start from scratch.
Okay, so I'm going to refer back to first and see if there are any outstanding questions from that. Okay, seems no. Feel free to send any questions in through the chat. We'll be checking them after each section and be able to answer those as we go along. So we have yet to do our Fiber 2. That's something we'll do here in a minute. And I believe we were down on slide 10. Okay, so we've talked a little bit about creating sensors from templates. We'll do the cut and paste here in a minute. We spoke about the color cues, at length about the concept of delta T and its importance, particularly as it relates between measurement range, wavelength range. And so we'll also go a little bit into the sensor calculation shorthand. So let's go ahead and go back to our Nlight example, and let's finish populating the sensors that were on our diagram. So also on Fiber 1 was an OS 3600. So we'll bring that in, and see Dan's doing such a great job. In honor of Dan, we'll call it a Dan OS 3600. Here again, we see that there are certain intrinsic coefficients that are brought in, and there are others that have to be populated. So we'll put in our same CTE of our substrate and our gauge factor, which we would bring in from our sensor information sheet. Go ahead.
I'd like to point out that even though those the ones with the dark blue background are what we would consider to be built-in coefficients, ideally they shouldn't change. They're not fixed in the interface. You can actually change them. If you do, the background color will change, letting you know that you have modified them. And once you return them to the value that was defaulted in the sensor template, it will return to the dark gray background. But if the need arises, you can modify those to whatever value you need.
Okay. So the OS 3600, as I mentioned before, it's an internally temperature compensated strain sensor. And so we won't have a need to identify another sensor for temperature compensation. Rather, we just need to tell Nlight which two FBGs on our measurement system are used for the OS 3600, specifically which is the temperature and which is the strain sensor. So this is something that you would also have from your sensor information sheet. Let me go ahead and bring up a copy of what a sensor information sheet looks like. Share Microsoft Word here. Okay, so this is for an OS 4300, which we'll be demonstrating next. But basically, you'd see your serial number, a nominal wavelength, a part number, and then the temperature expression, which of course our sensor templates in Nlight are going to bring that in for you. And then you'll see all of the coefficients here. For an OS 4300, there are actually five coefficients that are used. But for an OS 3600, you would see the nominal wavelength for the strain sensor, the nominal wavelength for the temperature sensor, so that you would know which of those to assign in Nlight. Okay. In our application, we know that our temperature sensor is also on channel 3, and that it's our first FBG on channel 3, or FBG C1, and that our strain sensor is our second FBG, which I can also filter. I have to filter. FBG C, well, I can't even get to it. There we go. FBG C2. All right, so now you see that these FBG C2 and C1 have been populated in the expression for delta T, which is our relative operating temperature for the 3600. That delta T is used in the calculation for the epsilon T0, or this is the thermal component of strain. The the perceived portion of the strain that's caused by temperature change only, and then that sub-expression is used in our total expression of the total strain, or the total change in wavelength seen by the FPG, minus that which is induced by temperature only, which in the end gives us our mechanical strain, which is our goal.
So that expression there shows a little bit of the convenience of using the template. Considerably more complex and more difficult to get correct, but with just a few clicks of the mouse, you can get an OS3600 up and operational.
Right. Okay, now with the same visual cues, we can click on the DAN 3600. We see in blue, that's our strain FPG. Indeed. And we see in gray, that's our temperature compensation FPG. And so now we can zoom in and make the appropriate changes. Since we're doing a lab demonstration, we know we're not going to see a tremendously wide temperature range. We're going to go ahead and narrow our operating temperature range of that FPG. Notice as I'm pulling these bin widths, it's changing the minimum on the table for the FPG, and it's also changing the relative T for this OS3600. So I'm going to drag that in to be plus or minus 20. If you're unable to achieve the resolution that you want by dragging, you can also use these click buttons on the left and right. This will adjust the maximum bin. This will adjust the minimum edge of the bin, and then you can click on the center to change the step size for fine-tuning. Okay, so now we have moved our operating temperature to plus or minus 20, and now what I really want to do is change my range and increase that for my strain range. So I'll grab the bin for the, again, the blue, implying that that's our strain FPG for this macro sensor, and drag its width until I achieve the plus or minus 1200 microstrain that I want to measure. Again, I can fine-tune that if I want to be very specific, or I can just drag to a nearby value. Okay? So very quickly, we've established an OS3600. Wavelength ranges are provisioned for both the temperature sensing and strain sensing FPGs to operate from a plus or minus 20 from ambient over a minus 1200 to plus 1200 microstrain range.
I'd like to point out here the importance of the relative T column on the sensor grid. That was a recent addition to Nlight. With, for example, an OS3600 where both of the peaks are integrated into one package, we don't define another sensor as we did in the first case with the 3100-4100 combination. So without the relative T column, it wouldn't be possible unless we had to create a dummy sensor for that internal peak to be able to view what that temperature range was. By integrating delta T and the relative temperature right into the user interface, we're able to present that information without the need to create a dummy sensor so that you would know what the range on the temperature was. It's all presented right there with the value of the strain.
If we explore this expression itself, this might be a good time to introduce some of our computational shorthand expressions. These are built into the expressions that the templates load, but they're also very convenient for use when creating your own expressions. In many cases, measurement values are computed based upon the current FPG value, the current FPG value minus the reference value, and the current FPG value minus the reference value over some nominal value. So these are three quantities that are commonly used in sensor expressions, and Nlight employs a series of shorthand expressions to realize those. Maybe this is a good time to demonstrate the help tab. Go ahead, Dan.
And the goal there being twofold. One, to make it easy to enter expressions if you're doing it manually. Something we didn't point out is that even though we have the templates now, you can still manually create your own expressions with all the different mathematical operations that we support, and you can combine them in any way that you need. And the other is to make what you see in the expression look more like what you see on the data sheet. So typically on a data sheet, you'll see that it's the normalized wavelength times the factor plus, an offset for the temperature compensation. So what the shorthands allow us to do is to present those expressions in a way that more closely mimics what you would see on a data sheet.
So now I'm looking at the built-in help on the user manual on the Help tab. And if I go into the sensor section, let's see. It is fair to say that the PDF is easier to navigate than is the HTML built into, here we go, it's right underneath this. So here's some of our sensor calibration shorthands. Again, here we know that strain is really, and this is, take this with a grain of salt, this is basically just showing a relationship here. This may not be 100% correct, but if strain were to be calculated by the wavelength minus the reference wavelength over the reference wavelength, then we can simplify that through a series of shorthands, and this is basically how the computations in Nlight, the syntax that Nlight will use. X_0 is the reference value for when the FPG was zeroed. For when the sensor was zeroed. So it's an FPG value that's stored within that particular sensor's records. X_D is the delta value, so that's the current value, X, minus the reference value, X_0. And then this X_normalized, X_N implies a normalized sensor, which is that delta sensor over the reference sensor, which of course expands to the current minus the reference over the reference. And so this whole expression that we start up here can really be simplified down to this one expression of lambda_normalized. And as Dan said, really what this does in many cases is allows you to enter that expression into a create sensor window so that it really resembles the sensor information sheet or the published expression for that particular optical sensor. Okay. So now we have added our 3 sensors on Fiber 1, and we've got our 2 sensors, which are absolute temperature sensors that we want to load on Fiber number 2. So those 2 sensors are both OS4300 sensors. I'm going to open up that expression, and I'm just going to name this first one OS4100_1. And you can see here that the expression's brought in, and it's a third-order polynomial, and it requires 4 coefficients as well as a lambda OS or a lambda offset. And so those expressions can be manually entered, or preferably, let me go back and show again what that sensor information sheet looks like.